So this is the event in 2013. Maybe you can notice that the entire mountain slope was eroded by debris flows and waters. And during this event, typhoon or cyclone in your terminology stayed near this island for a long time, and lots of rainfall continued in this island. And precipitation in one night was 824 millimeters, almost 1 meter. So this disaster happened. So long time rainfall is one of the recent problems. Next one is the event in 2015. I took this picture almost 1 month after the disaster. However, during the disaster, this was the situation. This was a terrible torrential flood. And this is new feature of climate. You can notice that rainfall areas made such vertical or north-south band. Low pressures traveled from south to north one by one. Several rainfall event traveled one by one. This means the river basin received lots of rainfalls continuously. One rainfall stopped, finished, and the next one came, and then another one came. So total rainfall was very bad, terrible, and all water came downstream to cause this torrential flood. And another one is in 2017 in Kyushu Island, western part of Japan. So certainly landslide is a consequence of heavy rainfall. And from this year, we came to know this phenomenon, linear precipitation zone. What does this mean? So, along this zone, many low pressures travel one by one. One low pressure goes away, the next one comes, and it brings another rainfall. Then one more comes, and then one more. So total rainfall along this river basin. Here, river basin is from west to east. So along this river basin, lots of rain came. So consequence was disasters. So linear precipitation zone is attracting a big concern among disaster mitigation people. And this was an event in 2018. So you may say, this is not a big disaster because river is small, but actually entire western half of Japan was affected by this heavy rainfall disasters. This is one of the disasters. And problem is like this. This is a Google view from the sky. And this
Ito na off ko lagi daw. Jangir, connection lost.
Okay, I will ask.
Now, sorry, connection is poor. This is my problem, not yours.
Sure.
Okay. Okay. So this is a Google view from the sky. So we studied when we were young that water in the river should be drained out into the sea, starting from the basin, and water comes into small river. Then water will go into the main rivers. But that idea is not correct. Now we have learned that now problem is here. Takashi River, main river, has very high water level. Therefore, drainage at the confluence point is not possible. So Oda River, tributary water cannot go out. Therefore, water level in the tributary becomes very high, overtop the levees. Also, local small rivers cannot drain water into this tributary river. So finally, entire basin is flooded. So we calculated the amount of water flow in tributaries, main rivers, but such calculation does not work anymore because of this backwater phenomena. This is a new problem. And last year, also near Tokyo, after this urban area was flooded, one problem was also scouring of pier foundation, but for urban area, this was a problem. Entire area was flooded. Why? Rainwater was not drained out into the river. This is a cross section. Okay, we are looking at this urban area, the river for drainage, but now water level in the river is very high. So how can we drain out this local water into the river? There was no pumping station, or sometimes pumping station too weak. So this water in the urban area remains here. So as a consequence, entire urban area was flooded. So now, after many bad experiences, we came to understand that drainage into big river it's an illusion, unfortunately. And this is an event in July this year. I was busy with it because of this disasters. And this is a consequence of Hitoyoshi city in July. And I took this picture after water level came to the third floor, about this level. So this is a terrible flood for local communities. So why water level was so high here? So this again, Google view. So Hitoyoshi city is here. It's a small basin in the mountain areas. And heavy rain came to this area because of linear precipitation zone. Then there's only one river that drains water into the sea. Problem is, this river channel is very small, while lots of water or rain occurred in the Hitoyoshi cities. So drainage channel is so small, so this area was totally flooded. The water level came up very quickly. So actually, we don't know how to mitigate this problem. So we are learning new things, new lessons from many bad experiences. Problem is, nowadays, bad experiences occur every year. Also, I don't know how impressive this is for you. Yemen, in my perception, Yemen is arid country, not much rainfall. But then I came to know that Yemen is attacked by cyclone, heavy rain. So I feel that climate is changing and many bad things are going on. If this idea is correct, then engineers should.
Network disrupted again. Dr. Jangir?
Yes.
Probably Taha's connection lost again.
Professor, unmute yourself.
Professor Towhata, you are muted. Please unmute yourself.
I'm sorry, there's some communication problem. Okay. So this is data from USA. Oh, no. This one. So global climate people insist that temperature.
Share the screen, please.
Can you see this?
Screen share.
What's going on?
You have to share again.
Not shared. I see. Okay.
Yeah.
Okay. Okay. So global temperature is going up with years. This is basic information. And some USA people report that number of strong hurricanes or this vertical axis is equivalent area of what destructions, damage size. Damage size is increasing. I'm just looking at the upper bound. Also, previously there are not many disasters, but nowadays there are many disasters per year. So they insist that global climate change is affecting the safety in our community. Temperature. Also, this is data from Japanese Meteorological Authority. Abbreviation is JMA. So northern hemisphere, southern hemisphere, in both parts of the Earth, temperature is going up every year. So this is consistent with NASA data. Then what about seawater? There is such data, informations. Seawater temperature is also going up with years. So higher sea temperature promotes evaporation of water. Higher air temperature allows more moisture to stay in the air. So there is more likelihood of heavy precipitations. This is true or not? This is a basic question. So rainfall patterns. Well, I studied lots of historical data in Japan first. I expect that some Bangladesh engineers can do similar study for your own country. So here, vertical axis is annual rainfall in Tokyo, and horizontal axis is here. In this diagram, actually there are not no long-term trend, just fluctuation. If you look at just short term from after 1970, maybe there is some increase, but actually in the past, there are always lower value, high value, low value, high value, those fluctuations. So this data is inconsistent with global climate change discussions. Also, now term of rainfall data is monthly precipitation in Tokyo for the past 140 years. Again, there's not much, no clear trend like this. There's just fluctuations. Now, time range is shorter. Now, this diagram shows maximum rainfall in 24 hours. That's the vertical axis. Every year, there is a maximum rainfall for 24 hours or daily rainfall. So now, there's some trend. Upper bound is increasing in the recent, say, 50 years. This may suggest that the risk of rainfall disaster is increasing in Japan. I don't know Bangladesh. Okay, then time range. So I would like to say that there's no long-term trend in annual and monthly rainfall records. But for shorter time period, rainfall per day power is probably increasing. Now I expand the range of study from Tokyo only to nationwide. AMEDAS, AMEDAS. This is a network of rainfall monitoring. There are 1,300 stations all over Japan. And I collected data. Vertical axis is rainfall intensity, millimeter per 24 hours. I don't work on months or annual. I'm interested in short time range. So how much maximum rainfall per day happened in each year? That's shown by black symbols. And upper bound is increasing. This means every year we have higher risk of very heavy short-term rain, one-day rainfall. And some people say, no. Number one of the country, number one record is too extreme. It occurs in a small area. We should pay attention to wider, bigger size of rainfall. So I say, okay. Then we go to number 10 rainfall. Number 1 and number 10. So I think I cover the good range of rainfall intensity. So also white symbols also going up with time. So I'd say that there is a clear risk of short-term heavy rain in Japan. And in Japan, one day heavy rain is bad enough to cause lots of troubles, landslides and floods. And this is governmental information, nationwide data. How many times rainfall exceeds 50 millimeters per hour? So there's such trend in the past 50 years. Until 1998, average trend was, let's say, 250 times per 1,300 stations of AMEDA system. However, after some year, in the 21st century, number of heavy rain increased. So again, I would like to say that the risk of short-term heavy rain is increasing. Also, not 50 millimeter, now 400 millimeter per hour. This is terrible rainfall. Oh no, sorry, 400 millimeter per day. Sorry, 400 per days. Now, not very clear, but there's some upper bound trend like this. We do have more risk of extremely heavy rain. It's more dangerous than in 20th century. So we are living in dangerous 21st century. I don't know the situation in Bangladesh. You can study this point. But I try to do very brief study on Bangladesh. I spent only 2 days, and I could not find much data. And most publications address only annual average rainfall. And there's probably the officers are not yet interested in extreme events. Extreme means precipitation per day or per hour. So I could not capture changing trend of strong rainfall except this one, change of maximum daily rainfall in Dhaka. I found this diagram, and according to this, daily rainfall, maximum daily rainfall is not changing, but in 21st century, there's two bad events, but this is not enough to support the idea of global climate change. This may be just fluctuation of the data. What about cyclones? This is a big problem for Bangladesh. So I found the data, wind speed of cyclones in Bangladesh. That's the vertical axis. So your wind is terrible. 200 kilometer, 250 kilometer per hour. That's very bad. And is there any long-term trend? This is also difficult to judge. But recently, there's more data of strong winds than 1970s, 80s, but mathematically or statistically, we cannot say.
Professor, you're disconnected again. Professor, yeah, you have to unmute. Professor, you have to unmute. Professor, you have to unmute.
Okay?
Yeah.
Okay, sorry. Communication poor. Okay. So this is Bangladesh. So also sea level, highest sea level is not increasing except these two data. So it's too early to draw any positive conclusions about global climate change effect in Bangladesh. But you can do better study, I'm very sure. But Italians are suffering from this problem. This is Venezia or Venice in Italy. This is a very important sightseeing spot. And this phenomenon is called high water, acqua alta in Italian. So this is a big problem, and this is a high water level during aqua alta in the past. So highest water level occurred in 1960s, but point is nowadays in the 21st century, number of aqua alta increased. It occurs more frequently than before. So Italians are talking about global climate change nowadays. And there is already pessimistic opinions about future. So this Stern reports insists that a number of inundation, flooding per year is increasing with years, and until the end of this century, every day Venezia will be flooded. This is very, very pessimistic opinions. But anyhow, there is some increasing trend in aqua alta phenomena. And there are some opinions about cause of this high water. Strong wind in the sea is a problem. Consolidation of the settlement, soil mechanics is another important cause. And then global warming. There are also studies, sea level changing in Adriatic Sea is like this, upper bound, lower bound. And then in Venezia, trend is shown by red colors. So in 1930s, 40s, 50s, 60s, sea level in Venezia came up. This is because of consolidation. Lots of water was pumped up. So everybody, you know very well about pumping problem, consolidation. So this happened in Venezia, and later pumping was banned. So now trend in Venezia is the same as the trend in the entire Adriatic Sea. So there possibly a global climate effects on the Venetian problem. Japan, maybe some of you were students in Japan, and they have experience of visiting this shrine, Itsukushima Shrine near Hiroshima. This shrine is 1,000 years old, and it is located on the shorelines. And recently, the problem of the submergence of the shrine. In the 21st century, the more frequency of flooding, inundation, submergence of the shrine than in the 20th century. So some people say, oh, this is evidence of sea level rising. But I would like to say that sea level rising is not so evident from engineering viewpoint. Scientists are talking about 5 millimeter rising, 1 centimeter rising. So from the engineering viewpoint, 50 centimeter rise is a big problem, but 1 centimeter, not a big problem. Then what is the problem of cause of flood? First, upper diagram shows the measured tidal level, sea level, changing with year. You may say that no, sea level is going up, tide level is going up. But actually, this is the consequence of local consolidations. So ground is sinking. Sinking at the site of tide gauge, not in this shrine. So sea level looks like going up, but actually, after
Professor, we cannot hear.
Probably connection lost.
Professor Towhata is in rural area now.
Connection lost again. But by the way, dear participants, Dr. Jangri mentioned that please rename someone I'm seeing, I can see guest or student ID. Here it's not relevant. Please rename. Just keep your name only.
Yeah, all should rename.
Yeah, I'm sorry for this problem. Can you hear me now?
Okay.
Yeah. Okay, then I was somewhere. Hmm? I was here. So sea level change is not visible yet from the engineering viewpoint. So I decided to review rainfall-induced disasters in Japan from 1945 to 2020. Actually, what's going on? I wanted to know, I wished to know what's going on in rainfall disasters every year. I don't want to just look at rainfall, disaster, landslide, flood. I wanted to know something behind that situations. Question is, rain-induced disasters are increasing nowadays because every year Japan suffers from rainfall disasters. Some people say, oh, this was not the case in 20th century. Once every 5 years, big disaster happened. But nowadays, every year we have big disaster. So they say global climate change is very bad nowadays, but I'm not very sure about that. The reason is, in the past, there are many heavy disasters. We just forget them. we clearly remember the disasters this year, last year. They are more impressive than those old disasters. So we are saying, nowadays we have many disasters. We are living in very dangerous 21st century, etc., etc. But the scientific approach to understand our risk, we should not rely on just impressions. So there is a need for more quantitative study about disasters. I already showed you this diagram. This is a number of heavy rain per year, increasing after 21st century. However, scientists, people of disaster science, they just talk only about rainfall intensity trends, like this diagram. They say now risk is very high, risk is very high. But we should also pay attention to our efforts. Engineers, you are engineers, we are engineers. Civil engineering did lots of job to mitigate disasters. What about our efforts? This is the structure of what's going on. Rainfall occurs, water comes into the river, then water comes to the human community. But civil engineers did lots of efforts to protect our community from water by constructing dams, levees, retarding basins, etc., etc. Many efforts are done. scientists don't pay attention to engineers' efforts. So in order to talk about risk increasing or decreasing, we should pay attention to both rainfall intensity and the quality of our human community. So first, so I collected information from 316 disasters over how many years? 75 years. So every year there are 4 or 5 disasters on average. Points of study. Intensity of rainfall. Strong rainfall is increasing in number or decreasing or no change. That's the question. But also we should study this quantitatively, the size of damage. Big disaster, oh, but no, that's not scientific. We need to make size of disaster, size of damage into numbers. Those numbers should be easy to obtain parameters. So I decided to work on number of damaged houses and also size of flooded areas. These two informations are released by governmental sections for independent for each disasters. Well, number of victims is not appropriate because people
connection is disrupted again. It's from our end. It's a problem from Towhata's end. Dr. Jahangir?
গ্রাম এলাকায় আছে তো ডিসকানেক্ট হয়ে গেছে।
এটা আমাদের দিকে তো কানেকশনের সমস্যা মনে হচ্ছে না নাকি
রুরাল এরিয়াতে গেছে আজকে শনিবার আমার বন্ধ হয় শনিবারে তো
না এনিওয়ে যেটুকু বললেন ক্লিয়ারলি শোনা গেছে যদিও মাঝখানে কয়েকবার ডিসক্রিপশন হচ্ছে আছে
Can you hear me?
Yes.
All right, I'm still there. I'm joining from all the way from United Kingdom, and I can hear you properly.
Okay. So our speaker is actually connected from a rural area. So that's the reason
I still believe he might rejoin, or he might be able to rejoin.
Yeah.
Professor Towhata is out of Japan, right? Dr. Jahangir, where is he now?
He's in Japan, but in
Rural
rural.
area, rural.
ইয়াসিন স্যার আসসালামু আলাইকুম আপনি আমার ছিলেন এক্সটার্নাল আমার নাম কামরুল হাসান আপনি আমার থিসিসের external supervisor ছিলেন supervisor না you were the interviewer in my undergraduate in 2000 so 20 years ago you just came from
20
Japan
years
I
ago.
think yeah exactly I think you just came from Japan at that time
Okay. So where are you now?
in Glasgow United Kingdom yeah
United Kingdom. Oh, very nice to hear you after so many.
nice to hear you assalamu alaikum again
Engineer Kamrul is now geotechnical engineer in United Kingdom.
yeah principal engineer I'm working yeah
Engineer. And also got the chartered.
How long?
yeah I'm a chartered engineer and fellow of Geological Society of London as well
কতদিন থেকে?
আমি পাশ করার এক সপ্তাহ পরে আসছি সো নিয়ারলি অনেক দিন আর 19 বছর
19 বছর
প্রায় 19 বছর স্যার
So you're already set. Anyway, it's nice that do you come to Bangladesh?
yeah quite a lot
Do you come?
but I keep in touch with Jahangir bhai
Because we
yeah
expect that whenever our expatriates come to their motherland, sometimes if they have time, we arrange for seminars in Buet.
yeah that will be a pleasure yeah
Time. Yes, if you have time.
Yeah.
Very sorry.
This back
Oh,
again.
okay.
So,
I'm very sorry for this problem. Oh, so
It's okay. We can hear. No problem. It's fine.
yeah, I hope so. So this is number of damaged houses during each event of heavy rain. So Japan was under very bad condition in 1950s, 60s, and 70s. One disaster destroyed 500,000 houses, maximum 600,000. But now, after 80s, situation changed because of engineers' efforts to construct levees, dams, etc. So flood became smaller. And particularly in 2010s, number of house damage is very small. Then my concern is this part. After 2017, damage size is increasing like this. So what's the meaning of this part? Before drawing this diagram, before collecting data, I was thinking, I imagined that damage was very bad became very bad in 70s. Then we had peaceful time in 90s. Then after 2000, the disaster became worse and worse. But actually, data is different. We had happy time. Japan had happy time until 2016. Then something is going on. But what is the reason for this? Also this another data, size of inundated area. Appearance is similar. Japan had happy time in the 21st century, but after 2012-13, damage is increasing. Then how powerful is rainfall in recent years? I think I showed you this diagram before, but I'd like to repeat it again. Rainfall intensity per 24 hours is increasing in the past 30 years. So rainfall is increasing, but actually damage was decreasing or small in 1990s and 2000. Only recently, 5-6 years, damage is increasing. So there is some difference in damage size and rainfall intensity. This is very strange, and I'm quite curious about this. So what is the causative mechanism mechanisms of rainfall disasters increasing in the recent years. Global warming increases rainfall intensity and more damage. This is what global climate scientists are talking about. But then question is, why was damage less until middle of 2010s? Rainfall was increasing, but damage was decreasing. Yeah, we have. So should we say that rain is extremely powerful only in the recent 5 years? No. According to data, rain is continuously getting stronger. So just data fluctuation, damage data is just fluctuating. And there is no reason. This is okay, possible. I cannot reject this. Another possibility is decay of social resistance against heavy rain, deterioration of levees, structures, community network, etc., etc. This is another possibility. Why decays? People rely on public service of safety. They say self-defense is not necessary. Government officers should work for people's safety because we are paying tax, etc., etc. They don't try to protect themselves. They are careless about safety. This is one possibility. Also, another possibility is deterioration of levees and other infrastructures. So I calculated the vulnerability index, VI. VI is defined by damage size divided by rainfall intensity. Scientists are just talking about rainfall intensity. This is increasing, rainfall intensity is increasing. But we should pay attention to damage size quantitatively and pay attention to infrastructure's quality. So first, I calculated vulnerability index in terms of flood area, size of flooded area, square kilometers, divided by maximum 24-hour rainfall. So this is a diagram. Appearance is a bit different. Vulnerability is decreasing in the recent 10 years. That means rainfall is getting stronger, but damage, size of flooded area is not so big as maximum rainfall implies. This is a good news, but actually damage is increasing. So there are still questions about this. Then what about vulnerability index in terms of house damage? Number of affected houses divided by maximum rainfall in 24.
Towhata has lost his connection again. Jahangir, it was supposed to be a 1 hour presentation.
Oh, now I'm getting accustomed to solving the problem. Sorry, can you see this?
Yes.
Okay, thank you. So I used to tell students, don't do this, don't erase unfavorable data, but I'm doing this in this diagram. If we erase this point, abnormal point, then we can say vulnerability was decreasing until 2011 or 12. Then vulnerability is increasing afterwards. Also, use of Ameda's national number one rainfall data is not good. Maybe extreme data, too extreme. So let's try to use number 10. But by erasing unfavorable data point, then we can say this. This is logarithmic plotting. So actually, difference between 100 and 300 are huge. So I may not be very fair. I'm just trying to do something. So very pessimistic scenario is like this. Actually, civil engineers have been doing lots of efforts to mitigate rainfall disasters by constructing dams, levees, also planting trees in mountains, etc., etc. But such efforts are not effective anymore because power of rainfall, global climate change overcomes human efforts. This is my most pessimistic scenario. This may be true, may not be true. Actually, I don't know. But anyhow, the disaster is increasing in the recent years. So engineers should think about how to mitigate disaster. So problems emerging now is bottom two issues. Decay of social resistance against heavy rain. Vulnerability is now increasing. Why decay happens? Because people don't care their own safety. They totally rely on public service of safety. No self-defense. And deterioration of levees and other infrastructures are getting weaker and weaker. Just look at this example in Tokyo. People don't care flood disasters. They are living carelessly in disaster vulnerable areas. This is a half 50% basement of condominium, and this building is facing the river. Actually, this area is specified as part of river channel. This place is not protected by levees, but people don't care. Actually, this is a levee. Building is on the left-hand side. So this building is inside levee, or inside the river channel. So why are they living here in such a dangerous place? Your people declined construction of new levee because they wanted nice river view. They say big levees destroys nice river view. So daily happiness is more important for people than their life. They say safety is a government duty, not their business. So I say that's a lack of care of high water. Another example like this, also this is near Tokyo. This is a river. Usually, water is very little. Actually, there's a big river 200 meters beyond this point. So backwater occurs, and lots of water can come into this small channel, and overtopping can destroy this community. So all careful, smart people, their condominium is uplifted by, say, 2 meters. So I think this place is safe, but next to this, the another group of careless people, they are living in the first floor. First floor is lower than ground level. So I'm very sure that this year, next month or next year, flood will.
We've lost our speaker again.
Kamrul,
জি জাকির ভাই আসসালামু আলাইকুম বলেন
Okay, Professor Towhata is back.
So
All right.
sorry, I spent only 30 seconds to recover. Now I know how to solve the problem.
okay.
Engineers should know how to solve the problem. We should learn from lessons.
Indeed, indeed.
We don't need differential equation. We don't need a computer to solve the
We don't
problem.
need scientists, we need engineers. Yeah, I agree.
Yeah.
Problem solver, yeah.
Yeah. So okay. So now I know how to solve the problem. I was looking at this, showing you this one. So natural levee used to protect this community from flood, but owner, landlord of this place was very careless. He didn't care the community's safety. He decided to start solar power business. So he removed natural levee from his own land and installed lots of solar batteries. And local people, local authorities asked him, please don't do that because levee is important for safety. But he did not listen. He insisted that disaster mitigation is a business of public sectors. This land is his own land. He can do whatever he wanted. And he removed the soil and installed solar batteries. And then high water came. So river flooded from this place in 2015. So this is also a good example, a bad example that the people don't care their own safety. They say disaster mitigation is the public sector's duty, not their duty. That's ridiculous. I come back to same place. This area is this area. Actually, levee is over there. So there are several houses, buildings, big RC buildings, standing, resting inside the river channel. So they don't care their own safety. Or even they don't know that they are living in a dangerous place. So the plot. Bad news is that people don't care their own safety. But from recent disasters, still there's good news. Good news is quality of existing levees is not yet deteriorated because a few failure by seepage. Overtopping is a bad phenomenon, but overtopping is a matter of levee constructions. We should construct high levees. Overtopping does not mean deterioration of the quality of levees. What is very bad is seepage of water through levees. Seepage piping through levee means there are many holes in the levees. Poor maintenance, lack of financial support. Actually, Japanese government didn't want to spend much money on disaster mitigation in the recent 10 years. So water can flow through animal holes, insect holes, etc., etc. This has to be avoided by allocating some financial support for maintenance, but in the recent past, government did not do that. But fortunately, seepage is not yet serious. That's a good news. So people is a problem. Then, just what time is it now? Oh, it's already 7:30. Oh, I have to. Sorry, but okay. Slope monitoring. This is my favorite topic. I have been developing technology for slope monitoring. Why do we have to monitor slope? Because during heavy rain, we should issue early warning of ultimate failure and let people evacuate. And there are too many vulnerable slopes in the hilly terrains in every country. And it's impossible to reinforce all of them with limited budget. So we should spend
Okay, he's back again.
Sure. No, sorry. So this empirical knowledge, HO virus, average number is 0.5. Don't please forget extremely big event, which we have more number of small landslides during heavy rains. So 0.5 means this distance is 2 times the height. So we should live beyond 2 times cliff height. This is a basic rule, but this is not always possible. Then what should we do? What we should do is install some sensor here and try to escape. Why? Or anyhow, this is what I'm trying to do, and I'm doing this already. But please don't forget this very simple sort of monitoring. Just we go to this place to monitor the space. But this is a classic idea, and we can work on very slow landslide movement, sliding 1 millimeter per month, 5 millimeters per year. But rainfall disaster occurs suddenly. It occurs within 2 hours, 3 hours only. Then this classic technology does not work. So this is actually famous field study by Professor Towhata, Kyoto University. He caused artificial rain in slope, and he monitored the displacement of the slope. Like this. The motion picture.
山林に人工的に雨を降らせて土砂崩れを起こし、土石流のメカニズムを検証する実験が行われました。実験は1時間に80ミリ前後の集中豪雨を想定しました。雨を降らせてから7時間後に およそ5メートルの範囲の土砂が土石流となって20メートル一気に崩れ落ちました。森林総合研究所は、
Okay. This is a big fun, but what significance is here? He recorded the slope displacement, minor displacement, changing with time. So final failure happened at 420 minutes, but 2 hours before, already there was some slope movement. So aim of monitoring is we should detect the small minor displacement and let people evacuate. After 2 hours, slope fails. Let's skip this. And big mountain collapse is interesting. Particularly scientists, engineers, even academicians are interested in big one. But big one is very rare in number. What actually kills us is small landslides. Actually, this is the statistics in Japan. Small landslide, big one. The small in number. Actually, 4 small landslide is the majority. So we try to detect small landslide, small 4, and evacuate people. That's the aim. Chittagon, what is the idea about this place? Dangerous. I don't want to live here. It's too dangerous. So idea of sensors like this. Maybe some of you are already familiar with this. We put just steel rod, just surface soil, 1 meter, 1.5.
Professor Towhata will be quickly back. He already learned how to get back. That's what he said. Dr. Jangir, let him continue to 5. Can we?
Okay.
Yeah.
Okay. The conclusion is practice like this. If rotation occurs faster than 0.1 degree per hour, we should issue evacuation order.
Professor, can you show the instrument again?
Oh, yes, sure. This one.
Yes.
Instrument is embedded here. And this is installation. And this is the antenna for communications. Sensor is underground. This is the piece for just wireless communication. Okay. So we did lots of studies. This is a study in China, joint study. And this is the angle versus time. So when the rate of rotation is 0.15 degree per hour, then slope failed. This is the first slope failure. So we did lots of studies like this. Then empirically, we got this magic number, 0.1 degree per hour, and slope will fail within 3 hours. There's no science. Everything is empirical. So let me skip this. This is another site in China, Three Gorge Dam site. And this slope was almost failing. So we installed sensors, and this results 0.13 degree per hour, then slope failed. And then this is a summary, 0.1 degree versus remaining time until failure. So if we issue evacuation order, then we have 1 hour, 2 hours, 3 hours until failure. So everything is empirical. Some people say, what is the effects of geology, rainfall intensity, etc., etc., about this relationship? Then I say, sorry, there are only only 6 or 7 data real failures. Only 6 other 120 sites did not fail. So only 6 and 7 data set is not enough to do more detailed studies. Also, this is the table example. We installed sensor in Tibet, China. Also, we are doing study in India, Bhutan, Sri Lanka, Australia, and we're trying to start activity in Brazil. But coronavirus problem does not allow me to go to Brazil. So this is Tibet. So there was a landslide in this part of mountain, and then heavy debris flow started from this place of Tibet. Problem is debris flow, mud flow started from this place in Tibet. Then material flowed across the Himalaya and came into Brahmaputra River in India, and you are staying somewhere underneath. So you may not be very safe. At least some part of Bangladesh may not be safe from Tibetan problems. So we should do monitoring. Let me skip this one because extensometer is very expensive equipment. Say 100 times more expensive. And we can install this at only one place across these cracks. So when you know the location crack, you know the size of landslide mass, then you can install this and get very precise data. Then this is very nice. But in rainfall-induced landslides, we don't know which part of mountain will fall down tonight. So number of data, number of sensors is important. We can install as many sensors as possible. And this is the data from my tilting sensor. This is the data from extensometer. Pattern is like this, go up and go laterally. This means first, my sensor captures information. Later on, extensometer captures the data. So I can issue warning, maybe 1 hour, 2 hours before extensometer. So people have extra 2 hours for evacuation. The cost is much, much cheaper. And let me skip this. Also, we are using sensor for self-protection, safety control in construction site. This is also very recent. This is the first publication. The landslide happened, then for reconstruction, we install sensors. Then again, this slope failed. But we I'm coming to the end. I'm very sorry for this trouble. I'm staying in mountain resort to take a rest. The communication network is poor, but I'm coming to the end. Australia. Okay, this is typical data from many sensors. Red color means tilting, toward the bottom of the slope. Blue color, green color means opposite rotations. So this is what's going on. Top has open cracks. So sensors tilts towards the open cracks. At the bottom, we have lateral pressure and sensors tilt downwards. In the middle, we have a rotation of soil along circular slip surface. So we have this direction of tilting. So sensors can capture such a movement, and then how to use multiple sensors for safety or practice. We can monitor displacement at many points, then we can detect most critical places. Here we can install safety measures such as rock bolts and piles, etc. Like this, and achieve good safety. This is a typical example of safety construction in China. We can do this efficiently. We can identify where we should do this. And this, so this is a summary. I'm sorry for many problems, but I discussed about issues of global climate change. Actually, study is ongoing. I expect also Bangladesh engineers are interested in global issues from practical viewpoint. And what with limited budget, early warning and evacuation is the key. Technology is developing now. I'm very sorry for many problems due to poor communication on my side, but I'd like to have some questions from your side. Thank you very much for your attention.
Thank you, Professor Towhata. Although there were disruptions, we could hear you. This presentation is obviously thought-provoking. Globally, there are a lot of disasters that we can see in the recent records. And I don't know, one thing, whether we did not have much record in the past, this may be one, because of the communications or information recording, maybe in the recent past, we have a lot of records or information sharing. Earlier, for example, you showed one flood in Yemen, it's an arid zone. Maybe, I'm not sure, but there could be in history, but we don't have much record. But even in Bangladesh, what we see that you showed one picture from Chittagong area, and I was born in Chittagong, and I remember I used to, when I was in school, I used to play in the hills because our bus stand from while returning from my school, there was went to college to collect other students, and there was a hill we used to play there. And what we see that human interference probably has caused much damage to the system, natural system. That's why we see a lot of slope failure in the hills nowadays. Otherwise, in the past, there was not much slope failure in the hills. One of the most damaging effect is maybe the vegetation, loss of vegetation. That's why with rainfall intensity, what you have showed, with rainfall intensity, probably this factor also need to be addressed. You tried to propose several indexes, vulnerability index, but still I think probably they do not represent all the phenomena. For example, in an area where habitation is small, but maybe intensity is high, but in that case, what we will record or what we will see from the data, that not much damage. Okay, but in another area, the picture may be different. That means the potential for damage. So probably what you say, the data need to be analyzed or not unfavorable data. I mean, those are all data, and probably they need to be separated with more information. Is that,
yeah.
do you feel that? Another thing, I have to ask you one question, that is about the monitoring. It's definitely important, but particularly in the hills, the monitoring system that is installed is mainly for shallow failure,
Yeah.
mainly for
Shallow
shallow
failure.
failure.
Yeah.
But in the hillsides, deep failure also occurs. In that case, probably we won't get the early warning, right? So one thing we need to first define or determine the risk level, where and to what level the risk exists. Is that how do you do that? How do you do that? Because where people live near the hills, that is one thing. But the other thing is whether there will be shallow failure or whether there will be deep failure. How can it be determined? Because all those tilting instrumentation, I think those for shallow failure. What is your idea about
Okay.
the deep failure?
I could not hear your voice because of again communication problem. But first you mentioned vegetation.
Yes.
Vegetation is also very important problem. I fully agree. You. Well, Japan had the same problem before when I was a kid, say many years ago. My hometown's mountain didn't have much trees because people was continuously cutting trees for fuels and also agricultural purposes. So then heavy rain brought lots of disasters. So government decided to start planting projects early in the middle of 20th century. And after 60 years, now mountains covered by trees. So I understand that the vegetation is important, but to complete this vegetation project, we have to be very, very patient for 50 years, 60 years. Trees needs
Long
lots of
time.
time.
That's also
Long time. But
part
we
of
have to,
planning. Okay.
if we don't start, we can never get results. So vegetation is very important. Now, problem is going on in Philippines, Malaysia, Indonesia, because people cut too many trees. That's first point. The second point is what do you say? Data is quite affected by population density, etc., etc. Maybe that's why my data looks strange sometimes. I have to bring more additional information. It takes time. Actually, government does not keep exact location of disaster very much. It's very difficult, impossible to find where landslide happened in 1960s, 70s. So there are some limitations. So that's what I would like to say. Then, what was your third point?
Deep failure and shallow failure.
I certainly, from the scientific viewpoint, big disasters, big landslides.
Audience there, if there are questions.
Yeah, I've got one question, basically. জি স্যার
দুই সপ্তাহ বা 3 সপ্তাহের মধ্যে একটা প্রেজেন্টেশন মানে তোমার ইউকের এক্সপেরিয়েন্সের উপর বেস করে এটা দিতে পারো হ্যাঁ এখানে
জি জি
Okay, Professor Towhata is back again, so I think there will be some more questions.
yeah I've got a very similar question as of Dr. Yasin sir.
Please.
Yeah, a deep-seated failure and shallow failure, or very similar
Yes, sir.
question. As a practicing engineer, we face the same problem. Rain or rainfall-induced slope failures are usually translational failure, whereas climate change induced failure would be deep-seated. And another challenge we face as a practicing engineer, although there is a translational failure, but there may be deep-seated failure being masked or being hidden. How do you combine these two phenomena with respect to these changes?
Well, thank you very much for the question. Yeah. So I have been saying that big deep-seated failure is interesting and important, but number of occurrences is small. So when I started development of inexpensive monitoring system, we decided to focus on small ones. Okay, suppose you cliff behind your house looks unstable, then you need inexpensive, cheap monitoring. You don't want to rely on lidars or INSAs, satellite photograph interpretation. They are too much for small scale community protections. Those highly advanced technologies good for big deep-seated failures, but that's a business of governmental sections with plenty of monies. For community basis, for community safety, we have to propose less expensive sensors. That's my practical viewpoint. But I don't insist on my viewpoint. I'm finding clients, but so you can go ahead with your own way. No problem. I'm quite flexible.
Yeah, thank you. Another, you defined a term called linear precipitation. Can you define that linear precipitation in terms of duration and intensity?
No. Linear precipitation zone detected only in recent times because meteorological radar is now able to find out the location of heavy rain here. Then scientists found a linear zone of strong rainfall. This moving like this. So at this point, one rain goes away, the next rain comes, then next rain comes. So total rainfall is terrible, 1,000.
All right. And another, not a question, but a observation as of, again, yes, it seems climate change is a very buzzword nowadays. But it is interesting to some extent to see there is not enough data to demonstrate or support that that is happening. As you have shared your studies, it is interesting to see there is not enough data to demonstrate, especially some regions like Bangladesh, to say that climate change is occurring, although it is a very buzzword. It's very interesting to see from your slides that you have shared. Any view from anyone from the audience, including Sir and Jangibhai? What's your view on that?
Professor, please unmute yourself.
Could you hear Professor Towhata? Hear the question, Professor Towhata?
Yeah. Should I repeat?
No, just wait a minute. Professor Towhata, please unmute.
Dr. Jahangir, so again, connection lost. So if he's back, please ask him again if he has heard it. We could hear the question. And I think there are questions from other participants also. Is there any other? Okay, he's back. Professor Towhata, could you hear the question?
No, I missed it. Please repeat it.
You missed it? Okay, Mr. Kamal, Engineer Kamal, please.
Yeah. I said, although climate change is a very buzzword, is a very popular word nowadays, but what you have shared that we can see that cannot be perhaps demonstrated or supported from the parametric studies or the studies you have shared with us. Especially for some regions like Bangladesh, that is true. Although we hear a lot about climate change, but unfortunately we cannot demonstrate through the studies or data you have showed that that is happening. So why is this buzzword of this climate change? Is it a myth? What's your view on that? Or
Still, actually, I'm not very sure. As far as I studied in the past week, Bangladesh does not yet have evidence of climate change.
yeah, that's I'm coming from. That any views, sir?
No, actually, what we can say, we see some phenomena. For
Do you? Okay.
example, Professor Towhata mentioned about landslides and heavy rainfall. What we see now, that the sea tide level is rising. So the areas that did not undergo the inundation even in 10, 20 years, now every year they get inundated. So
yeah, but inundation, don't put, you are soil engineer, so don't forget the consolidation problem as well.
Consolidation, all right.
Yeah, no, what I mean, the climate change effect, the sea water level rise. So it's a global thing, rainfall.
So no, sea inundation or sea level rising is not 100% climate change effect. Actually, ground may be going down.
Yes, that may be. Maybe relative movement, maybe it's downward.
So consolidation.
But we see some strange phenomena. We see strange phenomena. That's what draws our interest.
So actually, tide gauge elevation should be recorded. Tide gauge may be going down because of consolidations.
Yeah.
Yes.
Yeah, Professor, for that means we need very precise GPS or some instrument which can monitor the location or the point coordinate with respect to the global reference or the local reference.
Yes, with respect to rock outcrop, stable geology.
So I have a question, Professor, that you are doing some monitoring, low-cost monitoring to warn the people who are vulnerable for due to the slope failure. But can you do something like that? For example, in most of the part of the Bangladesh or many countries like this have no warning system. Now you will say, for example, continuous this much rainfall, that this, for example, this specific amount of rainfall can be a trigger point or the warning point that you have to evacuate in the specific some selected areas. Is it possible that in terms of millimeter of rain to warn the people?
Sorry, I missed some part of your question because again for communications. But actually, okay, for collaboration, you mean collaboration?
No, Dr. Jangir, please repeat your question. I think it's better.
Okay, I want to repeat my question.
Yes, please.
Okay, number one is that, for example, this is as a developing country, we have not, we don't have the such capacity to install the monitoring system in parts of the hilly area. So what we can do is do some research, or from your data, we can do something that some amount of rainfall, continuous rainfall, will induce the slope failure. Is it possible that in terms of rain, the warning system will be in terms of rain, not in terms of the monitoring data?
Yes. Actually, there are two types of early warnings, two philosophies.
Okay.
My philosophy is based on displacement monitoring.
Okay.
But another group goes to the rainfall threshold. They monitor 1 hour intensity of rainfall as well as total rainfall since the beginning of precipitations. So when rainfall amount exceeds some limit, then local government issues early warning. Many communities, many countries are doing that. The reason for that is cost. Just they have to monitor rainfall. It's very cheap. That's an advantage.
Yeah.
But problem is just they monitor rainfall. Warning does not care local geology. And the warning does not care the topography. Cliff, mountain, or beach, as you are staying now, behind your virtual background. Rainfall warning. Tell beach people to evacuate. Unnecessary. So people come to think that, okay, don't care warning. We are living in a safe place, something like that. False, what's it? Negative for something like that. People don't rely on such a warning afterwards. So, but rainfall threshold philosophy is cheap. That's good. So everything, there are no perfect things in the world.
Yeah. Yeah.
Okay, well, from cost consideration.
Can I participate?
Professor Shariful Islam, he is also doing research on flow protection and river training work. So you want to ask some question or want to?
And thank you very much. Actually, not question. Since I was actually in the first part of your presentation, and I had to leave after 1 hour to join my lecture. Actually, I had a class. He's not hearing me, I think, Sensei. Maybe again the connection is lost.
Yeah. Okay.
Just
Okay.
wait a little bit.
Okay, I'm back now.
Wait a little bit, we'll be back.
Okay. So Sensei,
Please.
can you hear me?
Yes, please.
Okay, I'm Shariful actually. So I met you several times before. Thank you very much for your very nice presentation. I was with your presentation until 1 hour, but I had to leave because I had to give my lecture. So maybe it may be repetition, but as Professor Jahangir was discussing, so you are right, because in Bangladesh, basically, especially for the northeastern part, where it is not mountain, actually is Haor area. Haor means depression. I mean, every year flooded due to rain, and also for the water comes from the, upper side from India. So in one project we are working with hydraulic experts. So they are doing modeling.
It's better to stop your video.
Okay. Actually we are.
Please.
I should repeat.
Keep the video off. Keep the video off. Keep the video off. Then
yes, I already.
The sound will be better.
Okay. I already off the video.
Go ahead, please.
Okay. So in that area also, as you mentioned, they are using this rainfall threshold model, and every year, especially for the agriculture. Because sometimes this flood is early flood, so they give warning to cut their rice and other crops. So it's working, but sometimes, as you told, that it's miss warning. So next year they don't, care about the warning. So that's why I think we must also develop, as you mentioned, considering the geology and topography. So it should be, we should consider this one thing. And just to share with you, we are doing some research I'm doing with my group for long term. Some of my students are also here. We are using one very special grass, which has very long root. It grows 2 to 3 meters in 6 months time, somewhere. So we are using this grass in our areas, to protect their villages and to protect their embankments and also the submersible roads.
Yeah.
And the specialty is that this grass can survive for 2 to 3 months underwater.
Oh.
So then when water goes back, so it again, grow. So in this way, in our Haur areas, we could save a lot of, village embankments and also the road embankments. It is working very good.
Yeah, very good. Wonderful.
Yes, and also now this ADB is applying this concept, my concept, in another country like Cambodia and other countries. So, and also,
sorry, can I ask one thing here, Shaheen Bhai or Sharif sir?
Yes.
I'm calling from the United Kingdom.
Really?
It is very interesting to see that your special grass that perhaps is called Vidbar or something. I saw your research. Yes. How confident are you to capture or to solve the deep-seated failure? Using those.
Okay, I'll come. Yes, it's a very good question and very fundamental. So I'll come to you. So
thank you.
And,
thank you.
So actually, so this I'm just to share, and also we are for our hills in the Chittagong Hill districts. We are using this. Especially, we use this in the refugee camps, Rohingya camps, and so this is working because this is very environment friendly. But we need a lot of, very deep scientific research to find the fundamentals and other details. So we are trying that. As
Dr. Shariful.
Yes.
Okay, I think if you have something to ask Professor Towhata, please.
Yes. I'm.
Yeah.
Yes.
Idea is good. Okay. I fully support your idea. Wonderful.
Okay. So as one of my colleagues asked me, so his question is valid because actually what actually I wanted to tell with Sensei, that our failures for the hills and for the slopes is not due to the mainly deep-seated failure. It is due to his subject is due to rainfall, because the heavy rainfall causes and due to the rain cut erosion every year. So this vegetation and others, this kind of method does not work for the deep-seated failure, but it works for the shallow failure, but in the long term, so it protects the hills and the other slopes. So this is the actually philosophy.
So I have the same philosophy. Deep-seated failure is difficult, but
yes, but in the long term, actually, this is not due to the deep-seated failure. It happens due to the continuous failure by surface erosion, and
weathering, many things.
Yes, so that was actually I wanted to highlight it. If you think that because from your long-term experience, so is it the right way or correct way that we can think together? So thank you very much, Sensei, for our the last day.
Professor.
Okay, so I'm done.
Professor Towhata, do you have any comment on Professor Shariful's information? He's lost again.
No, communication problem.
Communication.
Anyway, Shaheen Bhai, Assalamualaikum. আপনি আমার টিচার ছিলেন, again salam from Glasgow, United Kingdom. It's nice to hear you after a long time.
Okay, আপনি কোন ব্যাচের?
না আমি অনেক ছোট, আমি সাইফুল ভাইয়ের রুমমেট ছিলাম, আপনার ফ্রেন্ড।
Okay, Professor Towhata is back.
So we'll have a chat. We are working.
Professor Towhata is back.
Please call me.
Professor Towhata is back. Okay.
Yes.
Professor Towhata. So,
yes.
Do you have any comment on Professor Shariful's information? What he said about deep-seated failure and use of vertical grass?
Yeah. Wonderful.
Okay. I would like to ask you another thing. Since slope failure is progressive, failure in soil in most cases progressive. So what you are measuring, your tilt or deformation, so in 1 year there is 1 milli, 2 milli, 5 milli, and it doesn't mean the same thing in consecutive years, right? So in the first year, maybe 5 milli deformation is not a big deal or not a matter of concern, but maybe after 5 years, you need to monitor the summation of the deformation or total deformation. That's what.
certainly that what I'm measuring is summation during survey time only. Suppose I started it survey last year, then what I can get is only displacement in the past 2 years only. I cannot get idea of 5 year long term. No. Only during
So-
monitoring.
But is that not important when you start monitoring? And it should be cumulative up to say 5
Well-
years, 10 years.
Well, okay. You are talking about very traditional type of landslides.
Yes.
Traditional means big soil mass moves slowly every year. So at the top, headscarp cliff occurs, and cracks opens. Then soil comes down slowly, and finally affects the human community. So for such a landslide, actually we can identify the size of soil mass. Then we can install extensometers, or even we can do inserts, satellite surveys, radars. We have many advanced technologies. But my target is different. My target is rainfall-induced landslides.
Only rainfall. No,
Yeah, that's
in case of rainfall-induced landslide also, what I wanted to say that the deformation that occurs every year, is it not important?
No. Actually, most rainfall-induced landslides occur suddenly. Yesterday, there's no problem at all, no crack opened. Then today it's raining heavily because of cyclone, typhoon, and then 2 a.m. tomorrow.
Okay. So in that case, the phenomena is of smaller time span.
Yeah, very short time, only a few hours.
Few hours. So among the participants, are there any other questions from the participants? Dear participant, do you want to ask something else to Professor Towhata? I don't hear anyone's voice. Dr. Jahangir, so in this case, I think...
I find now none. So there is no questions.
Also, okay, it's already, our time is 5:10, but for Professor Towhata, it's becoming late. Discussed a lot. So Dr. Jahangir, can you conclude? So, okay. So since there is no more question, I think we need to conclude. Of course, as I've mentioned, this very interesting discussion, and I think the discussion will go on.
Email.
Okay.
Yeah. No hurry.
No, it's okay. No, would you like to share your slides or information? In that case, you can send it to Dr. Jahangir if.
Okay.
If someone asks for it, if someone asks for it.
Yeah, I'll send him PDF file of my presentation.
Yeah, okay, that would be very nice. And many thanks to you for being kind to deliver this presentation.
Yeah, I apologize for.
No, not at all, Sensei. It's okay. Although there were multiple disruptions due to poor network connection. But you report, due to your report, you could connect it very quickly, and we could hear you. At least I myself, I could hear whatever you say.
Same here. I think it was just less disruption, just only, it came back very good in a very short period of time.
I learned lessons. I learned lessons from disasters.
You could come back very quickly. Yeah. So many thanks to you, and we think we'll get continued support from you.
I wish to visit Bangladesh.
We would like to invite you
next year.
Whenever next year, will it be okay? I think
after coronavirus.
Yes.
Can I take this opportunity to say thank you to a professor, and thank you, sir, Yasin sir, Shine Bhai, and Jahangir Bhai as well.
Yes,
it was good to hear you after a long time, nearly 20 years.
And same is here. Thank you very much for joining us.
Thank you.
From the participants, and also